Okay, so we defined entropy earlier this week with this kind of honestly weak definition. It's important because it's a stepping stone, but a lot of stuff that we talked about on Wednesday was just kind of like, this is where we are going. We're building up sort of a bunch of stuff that will become. Does anybody remember what we were trying to invent from the very beginning of Monday or Wednesday? What was the beginning, the whole point of this chapter? Any guesses?
Oh, you're asking a question?
Yeah. What is the purpose of thermodynamics? Energy, yes. Something very specific about energy, though. Distribution of energy, yes, is very important. Conservation of energy, yes, very important.
Energy produced from reaction.
Wait, say it again.
Constant reactions and energy produced from reactions.
Yes. All of that all together, though, to predict something, though, about chemical reactions. Because we can measure energy. I'll just keep playing with my pen. We talked about how fast reactions are. Talked about how to make them faster, slower, kinetics. Sort of how fast you get from A to B. And that was kinetics. So we covered that. Ooh, there's equilibrium too, but, and in this sense, we do kind of want to explain equilibrium. Like, why are some things so reactant heavy? Why are other things really product heavy in terms of equilibrium, when they come to an equilibrium? So fundamental, I guess we take it for granted.
What's the original question?
We're getting there. I should just stand here more often. You guys talk a lot more. Why do some reactions happen and others don't?
Spontaneous and spontaneous.
No, that's the question that we're trying to answer. Yeah, is it spontaneous or not? Yeah, like some reactions are really product heavy. There's got to be a reason for that. And it has to do with energy, and it has to do with the equilibrium and the balance of molecules. Although I guess that kind of is like at the core of this question of thermodynamics, is like, why do reactions happen sometimes and other reactions don't happen? And as we looked at on Wednesday, like some reactions happen depending on the temperature. Even in terms of like physical processes sometimes, like freezing or melting. Wow. Now I've lost my train of thought. So the point of all of this is to figure out, like, is a reaction going to be spontaneous? So we were building upon that idea, like, of, oh, right, this is where I was going with that. Mechanical potential energy. We want to find the mechanical potential energy of chemical reactions. Like, mechanical potential energy is easy to predict. I'm not going to drop my nice pen. I'll drop this not nice pen, right? Like, if I hold this higher, like just by looking at it, we can tell that it has more mechanical potential energy. If I let go of it, we know what's going to happen, that this is going to fall. It's going to be spontaneous. And if I was a magician, I'd make it go up. But I'm not. Right? So for mechanical things, yeah, things fall towards the earth because of gravity. What is gravity? We don't want to get into it. But what is that same thing? What is the gravity for chemistry? What is the, in a sense, we're trying to find, how do we define a low point in energy Or is energy even a good way to define what this low point is? Which brought us all the way to entropy. And it turns out it's not really energy that's driving anything. And in a sense, I think you could think of entropy as the gravity of chemistry. It's like, what is entropy? It's disorder. Everything spreads out. We have this law of thermodynamics that entropy for the universe always increases. And so to figure out if a reaction is going to be spontaneous, we have to figure out if it's going to make the entropy of the universe increase. And I feel like entropy is also kind of as hard to explain as gravity, at least maybe in a Chem 2 class. So we came up with this definition, or came to this definition of entropy for a system, and had kind of these nebulous units of joules per Kelvin. But this is only in our narrow definition of a reversible process. And that reversible process, I think of it as being at the, like, it's the tipping point of that process happening or not happening, going forward or reversing. And it's exactly at the tipping point. And I think what gets lost in this definition is that entropy, kind of like heat, has to go somewhere, in a sense. If the entropy of my system changes, it has to in some way change the entropy of its surroundings. So this is the entropy of the system, but really as it relates to the surroundings, and it has these units of joules per Kelvin. And again, haven't really gotten to explaining what that means. Actually, I think I read this morning. This is, no, we don't need that for now. So when a substance melts, it absorbs its energy from its surroundings. By taking energy from the surroundings, it decreases the entropy of its surroundings. And when something melts, goes from a solid to a liquid, does its entropy increase or decrease? Increases, becomes more disordered. So we go from a solid to a liquid. That's an increase in entropy of the system plus delta S of the system. And especially when you think of, water and ice. Ice going to water in terms of energy, right? Is this endothermic or exothermic? Think about it, do you have to add heat to water to make, or to ice to make it melt? This is one, I mean, these all go back and forth, right? In one direction, it's exothermic. In the other direction, it's endothermic. To melt ice, it's endothermic. So we'd say, right, plus Q of the system. We're adding heat, have to add heat to the system. But where does that heat come from? It comes from the surroundings. So if this heat comes from the surroundings, I guess it's surroundings, the heat goes into the system. What does that do to the, I guess, the heat of the surroundings? Decreases. And what does it do to the entropy of the surroundings? Also decreases. So this is negative delta S for the surroundings. And when we define Q, or when we define delta S as delta S of the system equals Q of the reversible process divided by T, that has to be at the tipping point temperature. So for freezing, it would be in Kelvin, right? 273 Kelvin. And the amount of heat would be really the delta H of fusion. And so we can actually calculate that, and that was what that Oh shoot, is it positive or negative? Depends on which way you're going. 22 joules per Kelvin. So if we're thinking about the ice melting at this temperature of 273, then the positive delta S of the system would be 22 joules per Kelvin. The negative delta S for the surroundings is negative 22 joules per Kelvin. And so the energy of the universe doesn't change because that's what's happening at that tipping point. It's not freezing, it's not melting. If it did start to freeze, then it would start to shift in one way or the one way. But if it started to melt, it would go, or if it starts to freeze, it goes one way. If it starts to melt, it goes the other way. But at that tipping point is really where we're defining, or where this definition defines the delta S of the system, is how is it going to affect the surroundings? And so really what we need to think about then, if we want to know if this is going to be spontaneous or not, if it's going to increase the entropy of the universe or decrease the entropy of the universe, and therefore be spontaneous, is how and why is Kelvin part of this, and what happens when we start changing the temperature as this works. So we need to know, like, we know that 273 is for my system. That's like the tipping point, melting and freezing. But what about for the rest of the room? What does that say about the entropy of the rest of the room at 273 or above 273, below 273? And so really we need a definition of that entropy. Let me calculate some entropies here. Oh yeah, so we did that. We'll come back to that actually. Actually, did we cover these slides? I want to get to the math definition. We'll come back to this very soon. So again, when we're exchanging heat between the system and the surroundings, it's really, did I say exchanging entropy? We're exchanging heat. And because of this exchange of heat, we're either concentrating or dispersing energy, and that's increasing or decreasing entropy. So for an exothermic process where Q of the system is negative, right, heat leaves the system, that has to go into the surroundings. If I add heat to the surroundings, that increases the entropy of the surroundings. If I have an endothermic process, it's absorbing heat. That's removing heat from the surroundings, which decreases the entropy of the surroundings. And we could use this relationship to come up with a better definition of what the delta S of the surroundings actually is. So we know that the delta S of the surroundings is proportional to temperature. And I know that because of that, I know that my delta S of the system, and this should really be written as, or my Q of the system, this should really be written as negative outside parentheses Q of the system divided by temperature. And really the things that we're combining here is that if I have a negative Q of my system, that increases the heat in the surroundings. So then that would be a positive delta S surroundings. If I have a positive Q of the system, so an endothermic reaction, then that's negative delta S of the surroundings. We can't have, we're using temperature in Kelvin here, so absolute temperature. So we can't have temperature changing the sign. So the sign of, really the sign of whether or not I have an exothermic or endothermic process is what determines the change in the entropy of the surroundings. So if I have an exothermic reaction, then Q of the system is negative, so it's negative times negative Q of the system divided by the temperature. And if it's endothermic, I'm going to separate these with lines, then it's still a negative on the outside of the parentheses, but now my Q of the system's positive divided by the temperature. And then the important part here is that it's divided by the temperature. And not the temperature at the tipping point, but the temperature of the surroundings. So the higher that my temperature is, really the less that the Q of the system matters for the magnitude of delta S of the surroundings. And as long as we're at constant pressure and temperature, which I think should just be an asterisk here, we can use delta H of the system instead of having to measure the specific Q of the reaction. Because the constant pressure and temperature, yeah, is the coffee cup calorimeter situation. Yeah. So the way that we can use this then is in going back to these graphs. And actually, wait, no, I want to go to this graph. I made a thing. So when we're at, make this at 0. So delta S total is 0. And I'm at, this is for water. So for water, that Q that we calculate at the tipping point is a negative, and this is for water freezing. So it's freezing, it's an exothermic process, which means it's releasing heat into the surroundings. But it also means that it's going from a liquid to a solid, so its entropy decreases. And that's why it's negative 22 joules per Kelvin. So if I decrease the temperature, right now it's like, well, technically it's not spontaneous or non-spontaneous. So if I decrease the temperature here, then the delta S of the surroundings will be increased by that heat released from the freezing of the water. So even though my system, and actually when I slide this thing around, right, the system doesn't change. The entropy change to the system only depends on how many of those microstates that I end up with. And since I'm going from liquid, which has more microstates than solid, that entropy is always decreasing by the same amount. And it depends on how many moles that I'm doing with. So this is like per 1 mole. What changes is how much that affects the surroundings. If the surroundings are already really hot, and I go up to the high end here, then, well, that was delayed. Then the heat in the surroundings, there's already so much energy in the surroundings that adding a little bit more heat doesn't do very much for spreading out the energy. So the entropy increase is small. And actually, we could do math for this. So if this is at high temperatures, delta S of the system for freezing is negative 22 joules per Kelvin. And that's not like something you need to memorize. It's just, we're just going to keep using that same number so I don't have to calculate other numbers. So negative 22 joules per Kelvin, that's fixed. But when we're calculating the delta S of the surroundings, the new definition that we had was negative, and this should also be negative. And then inside of that parentheses, delta H divided by the temperature. So this is delta S surroundings. The delta H of, in this case, since we're talking about freezing, is the delta H fusion, which is normally in kilojoules, but we want it in joules for this. So it's 6,010 joules, and that is exothermic for freezing, or delta H of fusion from last semester. It's the heat released by freezing water or melting water, or I guess in this case, since I'm talking about water, right? Delta H of fusion is the heat change, whether you're freezing or melting. So if I plug this in up here, negative times negative 6,010 joules, and then divide that by the temperature. And here we're saying it's a high temperature. So I don't know, let's just do 300 Kelvin because that's easy. And not even that high. But it's higher than 273, which is important. So this equals 20.0 joules per Kelvin. And that number is positive and smaller than the delta S of my system, which was negative 22. So if I do this at, so we calculate, right, this delta S of the surroundings at 300 Kelvin, it's 20. What do you think it is at 273? Positive 22. That's the tipping point. The higher the temperature gets, the more I'm dividing that delta H, the smaller it gets, the less of that heat that gets added to the surroundings matters for changing the entropy. And so overall, the entropy decreases for the universe. And so this is non-spontaneous. If we do the same calculation but change the temperature, delta S of the system, we're still talking about freezing. It's still negative 22 joules per Kelvin. And this is still going to be negative times negative 6,010 joules. But now divided by some temperature below 273. Let's just do 250. So that's 24 joules per Kelvin. And so if I divide it by a smaller temperature, I get a larger number. And if that larger number is larger than the decrease in entropy for my system, then the entropy of the universe increases. So think about this. This is for freezing. How does this change if it's instead melting? Yeah. It actually literally just changes all the signs. Because, right, if I'm melting, I'm going from a solid to a liquid, the entropy of my system is increasing. So that negative 22 becomes positive 22. It also means that now instead of delta H diffusion for freezing, it's for melting, which just changes the sign. Which means that there's now a positive in here, which makes it overall negative, and this would become negative 24, oh, negative, still getting used to that. Negative, this would be positive, positive, the bars are flipped. And so the conditions that that process is spontaneous at also flips. I'm going to undo those because that's going to be confusing later. All right, so let's calculate this for something else. So if we think about this reaction, calculate the entropy change in the surroundings associated with the reaction occurring at 25 degrees Celsius. So how do I calculate the entropy of the surroundings? Yeah, negative. And in my personal and professional opinion, you should put that negative outside of parentheses so you don't forget that it's not, that like it's part of the equation. And you put, if you have a negative delta H, you put a negative delta H in there and then multiply it by a negative. So my delta H of this reaction, this is going to be negative. And actually for this problem, it doesn't really matter, but this should be in joules. And then divided by temperature in Kelvin, which is 298. I guess the practice is good. So it's negative 547 joules per Kelvin. So is the entropy of the surroundings increasing or decreasing? Decreasing. Negative joules per Kelvin, decreasing. Now, determine the sign of the entropy change for the system.
The entropy of the surrounding is decreasing, the system is.
Not necessarily. So like before we knew that for freezing or melting, we could say how that was going to change. And so we knew how the entropy of the surroundings was changing. Wait. Yeah, I think the more important thing here is the moles of gas. Yeah, at first I thought, it's like, you can't like rely on that, but because we're using the delta H of the reaction, although not necessarily, delta H is just the change in the heat of the reaction, which is going to affect the entropy of the surroundings. But we want to know the entropy change for the system. But yeah, it's from the moles of the gas. So like up here, even this negative 22 joules per Kelvin, that's calculated from the delta H. But the sign of delta H, well, the sign of delta H depends on the direction of the thing. but the entropy and the energy are not necessarily tied. So we use the enthalpy, the heat change, for the reaction to determine how the surroundings are going to change. We need to know, is my system actually going to be increasing in entropy or decreasing in entropy as that happens? And for that, you need to look at the reaction itself. So and this is kind of the leap from talking about a physical process to a chemical process. Because the physical processes, they always change spontaneity, like going from melting, freezing, boiling, condensing. They always change spontaneity depending on temperature. But for a chemical process, it might not change from spontaneous to non-spontaneous depending on temperature. Because the reverse of this would also flip the sign of delta H, but also flips whether or not it's increasing in entropy or decreasing in entropy itself. So this reaction is endothermic. And over here I have 3 moles of gas to 2 moles of gas. And so decreasing the number of particles decreases the number of microstates, which means entropy is decreasing. So this is negative delta S of the, I'm going to do that a lot, system. So delta S of the universe is delta S of the system. And we know that delta S of the system, even though we don't know exactly what it is going to be negative. And we add that to the delta S of the surroundings, which is negative 547 joules per Kelvin. A negative plus a negative. Can that ever be positive? No. It's like here, it doesn't matter what I change the temperature to. My process is always going to be non-spontaneous. Or this chemical reaction will always be non-spontaneous, high temperatures or low temperatures. Because if I change it to a higher temperature, sure, the delta S of the system, or sorry, the delta S of the surroundings will be smaller, but it's still a negative number, and I'm still adding that to another negative number. And so that's not going to change whether it's spontaneous. If I do a smaller or lower temperature, I'm dividing by a smaller number, but it's still negative plus a negative, so it's always negative.
So would synthesis reaction usually be negative in entropy because you're going from more moles to less moles when you combine two things? Like sodium chloride, with no sodium, with a mole of chlorine, like 2 moles to 1 mole.
Yeah, I think most synthesis reactions will probably decrease in entropy. But you could go from
But that doesn't,
2 complicated molecules that make a lot of smaller, like a single type of a lot of smaller molecules. That could be an increase in entropy, but also the combination of sodium and chlorine. So then the other thing you got to look at is like, okay, well that's a decrease in entropy to go from Na and Cl down to NaCl.
but that doesn't necessarily mean the entropy of the surroundings is decreasing.
So that reaction is highly exothermic. Whereas this is a synthesis reaction that's also endothermic. So my process goes from 3 moles to 2 moles. That's a decrease in entropy. And it's also absorbing energy from the surroundings, which makes it
Sodium chloride would
decrease the surroundings.
release the
Right. So I'm going from like more molecules to fewer molecules, but I'm releasing lots of energy. So then in that case, I would have positive delta H, positive entropy of the surroundings.
which could result in either a negative or a positive
Yeah.
entropy, first depending on the ratio.
Yeah. It would be 2n plus. But this is going to be a negative delta H because it's exothermic. So then delta S of the universe equals, and again, going from more molecules to fewer molecules, this is going to be a negative delta S of the system, but it's going to be plus a, and I'm going to, if you'll allow me, just plug this in, divided by whatever the temperature is. So now it's positive delta H divided by temperature. And so we get basically a negative plus a positive, and that positive magnitude depends on temperature. So at low temperatures, this positive will be bigger. At high temperatures, that positive will be smaller. And so that will flip with temperature. And that was an excellent question because it's a perfect segue into plugging this together to give us Gibbs free energy. So like literally what I did to there is taking this reaction and saying like, okay, well, let's skip a step. If I know that the delta S of the surroundings, at least within a closed-ish system, is going to depend on how my reaction changes its surroundings, then I can just plug in this negative delta H of the system divided by temperature for my delta S of the surroundings. The delta S of the universe, delta S of the system, divided by temperature. And this is just like a common thing in any chemical or in any equation. Like if we can get rid of a fraction and have it not be in there, then a lot of the times we do that. So multiply both sides by negative t. So this is negative t delta S of the universe equals negative t delta S of the system. Yeah, I'm going to do that so many times. Actually, no, because we get to stop writing system after this. Plus delta H of the system. And actually, even just by talking about these last few examples, you can see how like sometimes the spontaneity depends on the temperature. It'll be spontaneous at high temperatures, spontaneous at low temperatures, but also sometimes it's just non-spontaneous. And so in a sense, by like just thinking about entropy and how my chemical reaction affects its surroundings and how that affects the universe, we've kind of maybe stumbled upon in some ways this chemical potential energy, which is known as Gibbs free energy. This is the analogous thing to mechanical potential energy. It is not as straightforward as hold something up high, drop it, and it falls. But it is still something that we can quantify. And so we take that negative t delta S of the universe, we drop all of the SYS, the system parts, because we're talking about just the system now. We've removed sort of the surroundings, or we've at least abstracted it. And we get the equation for Gibbs free energy. G equals enthalpy minus temperature times entropy. Um, Wait, what does this want me to write? I think it just wants me to write. Oh, at constant temperature. Oh, if T is a constant, then it drops. Yeah, because if there's no enthalpy, then there's not a change in temperature. Yeah, so the change in Gibbs free energy is equal to negative T delta S. And so essentially what we did by plugging numbers in for like sodium chloride or for other things is what this equation does by itself. So we found it. We found the magical thing. You've passed Chem 2. Congratulations. We did it. We discovered El Dorado. If only. And since we're pretty much out of time here, I think what I want to leave you with then is to try and keep this bigger picture in mind of what Gibbs free energy means, that it is this mechanical potential energy that depends on the system and how the entropy changes there, but how the entropy change there can create heat and change the surroundings, because don't know why I just realized it sort of midway through this last semester. I think one of the hardest things, actually, I've realized it before, but haven't emphasized it as much. It's the hardest thing about chemistry is that there are lots of equations and it's really, really easy to focus on, oh, these equations, these calculations, this is what I have to do here, and lose sight of the bigger picture and the context. Like, well, why am I doing that? Because the thing with a lot of the chemical or the equations in chemistry, as you well know, hopefully at this point, the equations are all kind of the same. The application depends on the situation. And that's what makes it complicated and hard, is when you're not keeping in mind of, well, what's happening in the solution, and you just see, well, I've got molarities and moles and there's a Ka, so I'm just gonna throw this into an ice table or throw this into a Henderson-Hasselbalch equation. Because maybe it's a buffer. I think the same thing applies to Gibbs free energy, and especially now that we have this sort of single equation, and we'll be using it in different ways and using it also in relation to equilibrium. Don't lose sight of why this equation exists and what it's describing, because you can forget, and just apply it like a hammer. One of my favorite sayings is, to the man with a hammer, everything is a nail. If you have a single tool, try to use that tool on everything, whether or not it's the right tool. So I have office hours now. I might have to run to lunch, like go and pick it up and bring it back. But if you want to look at your